Next speaker is Joonkyung Lee, who is a postdoc researcher at UCL. And he'll talk on majority dynamics on sparse random graphs, joint work with, I'm not sure I can read the first name, but Chakraborty, Han Kim, and Tran.
Okay, yeah, thanks a lot for the introduction, and yeah, thanks a lot for the invitation. It's my great pleasure to give a talk. I mean, I'd be actually happier if I could visit Moscow, but yeah, someday, yeah. Yeah, so yeah, this is joint work with Debsomya Chakraborty and Tuan Tran, who are at IBS in South Korea, and Jonghan Kim, who's at KIAS, also in South Korea. Yeah, so yeah, I'm going to talk about majority dynamics. So let me talk about what that is. So what's majority dynamics? So it's a model that, so it's a graphical process that models some sort of social behavior, which means, so suppose you have two choices, blue and red, nothing seriously political here. Okay, so you have two choices, blue and red, and you have certain connections with friends. And if, say, a majority of your friends support one party, say blue, then it's fairly likely that you are more inclined to support blue too. That's the nature. So yeah, this majority dynamics really models such a social behavior, which means, so here I've got some examples. So firstly, with this guy, I look at the neighbors of the color of neighbors, red and blue. And for example, for this vertex here, there are two red neighbors and one blue neighbor. So the majority is red. So on the next day, this one turns red. And so on. I do this simultaneously for every vertex. So for the other vertices, say this one, so it sees one blue neighbor and one red neighbor, which means tie, and then it just remains the same. So it will remain red. And the same thing happens for the other red vertex. And what happens for this guy is the only neighbor is blue, so it remains blue. So this is the situation in the next day. So this is day one. And the signs, so I'm gonna say the blues are basically +1 or -1. So I can also say that the blues represent some value +1 and reds represent the values -1 assigned to vertices. Okay, so this is how we play this game. So if I repeat, then for this guy, for the next day, so the majority is again red. So this one remains red on the next day. And then what happens for the others? Well, the other two guys here also remains red. And what about this one? So because the only neighbor is now red, so it turns red on the second day. And yeah, all vertices are now red. So I'm gonna say whoops, it's too thick. So I'm gonna say unanimity is achieved in this case. So it's 100% agreement, basically. Okay, let's see another example. So what if I delete one edge here to play with this, this one over here? Then what happens? Well, I can just play the same game. The majority of the neighbors of the central vertex is red, whereas the other leaves turn blue, right? And then what happens in the next day is exactly the opposite. So now all the leaves are blue. So the central vertex turns blue, and then the leaves turn red. And what happens in the next day? What happens is exactly the reverse. So it turns from this state to the previous one, and so on. So it oscillates between the two states. And a classical result by Goles and Olivers in the 80s says that given any finite graph G, and given any initial assignment S naught, which means I assign some plus minus one signs to the vertices of G, then the majority dynamics converges to a periodic behavior of length at most 2. So you've just seen the two possible cases already. So here, if unanimity is achieved, then no matter how I play the game, it should just stick to unanimity, right? Yeah, and you've also seen this example that oscillates between the two states. So their theorem says that, yeah, this is essentially all the cases you can expect. Yeah, so we are interested in analyzing these like eventual behavior of majority dynamics. And there are two basic things to set up, as you've already seen. So we have to set up the graph itself. So this is my graph. And well, there are many choices, but I'm primarily interested in G and P. Yes, so the most interesting example in probabilistic combinatorics would be GNP, the Erdős-Renyi random graph. Or it could be a pseudo-random graph, like sparse pseudo-random graph. For example, like ND lambda graph, if you know the definition. Or it could be grids or tori, and so on. There are numerous choices, but I am concerned mostly with GNP throughout this talk. And what about the initial S naught? Well, again, in the language of probabilistic combinatorics, the most natural example one can consider is the random plus minus one assignment. So you just flip a fair coin for every vertex to decide the color, the initial color. Or you could also think about some sort of sharper model saying, let's say I put plus minus ones as equal as possible. Yeah, which means the number of plus ones and minus ones are as equal as possible. Yeah, etc., etc. Yeah, so again, I'm primarily concerned with these random plus minus one assignment throughout this talk. Yeah, so yeah, we're gonna focus on GNP plus the random plus minus one assignment. Okay, so this is basic setting. So do you have any questions so far? No, everything's clear? Okay, let's move on. So in this setting, the first in-depth study was done by Benyamini, Chan, O'Donnell, Tammuz, and Tan a few years ago. So as I said, my G is GNP and S naught being random plus minus one. Then what they conjectured is if my P is asymptotically larger than 1 over n, then what happens is the majority dynamics converges to 99% agreement. So you can essentially think this 99% agreement as the unanimity I mentioned. And yeah, so here 99% agreement is somewhat necessary because of isolated vertices. So if my P is smaller than log n over n, then there are isolated vertices with high probability, right? So, and that isolated vertices would never change their colors. So 99% agreement is somewhat the best one can expect, but you can just conceptually think this as a version of unanimity, something closer to unanimity. And what they conjectured for these very sparse random graph was it does not. So this doesn't converge to 99% agreement. What they conjectured is actually slightly stronger than this. So they actually conjecture that it would be approximately 50-50 case. So you approximately have, yeah, if your average degree is bounded, then you approximately have the same number of plus ones and minus ones eventually. So
can I ask a question? So here you mean that for every C, it does not, it is a 50-50?
Yeah. For any,
because for like small C, it is obvious more or less.
Yeah. For any fixed, any fixed constant C.
Okay.
Yeah. And they gave some positive evidence for the conjecture. So for the first part, what they proved is if P is asymptotically larger than 1 over square root of n, then, okay, so I should have mentioned that all these are with high probability statements. Yeah, you would have assumed that, yeah. So, okay, let me get back to the work by these 5 people. Yeah, if P is asymptotically larger than 1 over square root of n, and then what they proved is the majority dynamics converges to unanimity with probability at least 0.4. Yeah, so it's not yet with high probability. And what they proved for this particular case, actually, I'm cheating here. What they proved is, in fact, for the random full regular graph. So, yeah, so this is a bit cheating. And what they proved for the random full regular graph is that the majority dynamics does not converge to 99% agreement with high probability. Yeah, so this is some sort of weak positive evidences for their conjecture. And later on, last year, actually it's archived 2 years ago, but Found2Lucky's Mi-Hyun Kang and Tamash Makai proved that through the following. So they basically pushed this probability of 0.4 to with high probability. So what they proved, to summarize, is if P is asymptotically larger than 1 over square root of n, then your majority dynamics converges to unanimity with high probability. But this is still, there's still a substantial gap between this bound 1 over square root of n and the conjecture bound 1 over n. Yeah. And since then, there were 2 different proofs of this theorem by Found2Lucky's, Kang and Makai. One by Lin Tran and Vu, and the other by Berkowitz and Devlin. Yeah, so here he's not Tran, so not my Tran. So yeah, but here Vu is Van Vu. Yeah, so what they considered is the sharper model that I briefly mentioned. So what they considered instead of this random plus minus one initial assignment is they just fixed the number of plus ones and minus ones. Minus ones, I mean, they fixed the discrepancy between the number of plus ones and minus ones as a fixed number, say C. So the discrepancy being C. Yeah, and then they studied what happens if I have slightly more plus minus one than minus ones in the setting of G_n_half or G_n_p for sparser P. Yeah, and by analyzing this somewhat sharper model, they managed to give an alternative, two alternative proofs of this theorem by Vantoulakis, Kang, and Mackay. However, none of these results actually broke this 1/√n barrier. And later, Celik, Dubak, and Vantoulakis wrote in their paper on the relevant variants of this problem. They wrote that it seems that the range P smaller than 1/√n, what was the term? Yeah, imposes immense complications. So this is exactly what they wrote. Yeah, and my result with Deb Chakraborty, Jong-Han Kim, and Tuan Chan states the following: if my P is at most some constant times 1/√n, and at least some other constant times log n/n to the 3/5, then the majority dynamics converges to unanimity with high probability. And hence, we break this 1/√n barrier for the first time. Okay, so this is our result. And yeah, for the remaining time, let me tell you a little bit about our proofs. But to that end, I have to introduce this heuristic behind the conjecture of these 5 people, Binyamini, Chan, O'Donnell, Tamus, and Tan. Okay, what's their heuristic is this? So let me just state their slogan. So their slogan is the bias. So the bias of the plus ones and minus ones then can be obviously quantified by the sum of STs over all vertices, right? And well, to eliminate the direction, I can just put the absolute value. And then what their slope. Sorry?
Can you remind us what was STV?
Oh, okay. So S0 is the initial assignment of plus minus ones. And I play this majority dynamics to obtain S1 on the next day, and then S2 on the next day, and so on. Yeah. So given the fixed graph GNP and S0, so I just keep updating the colors by using according to the rule of majority dynamics. So that should become S1, S2, and so on. So if unanimity is achieved, then this number should be n. Yeah, because all the vertices are either +1 or -1. Yeah, so that's ST. Okay, so this is the bias, and the slogan says that this should expand. So it expands by a factor of square root of NP at each step. So as t increases, so step by step, this bias should expand by a factor of square root of NP. So why is this true? I mean, this is not really mathematically true, but they believe that it's true. Okay, why we should believe this? So here's the punchline. So here, suppose for S naught, so I'm considering an alternative model that's sort of a toy model for the majority dynamics itself. So I'm gonna cheat a lot by resampling the edges every time. So every day I'm gonna resample the edges, which is not true. So in the real problem, I'm allowed to sample the edges only once and then just play the dynamics, right? Yeah, but let's just cheat to get the maximum possible independence. Okay, so here's my like sample the vertices. So what's happening for the first day is so let me just stick to some sort of bipartite model for convenience. So for each vertex, I'm gonna see some blue neighbors and red neighbors that are independently at random with probability p. So the edge probabilities are p. Yeah. And then what will happen is, say for this guy, my x phi is basically the binomial blue times p. So this is the number of blue neighbors. And my y phi is the binomial, the number of red vertices p. Yeah, so this is the number of red neighbors, and they're independent. And I'm gonna decide the color of my vertex v for the first day according to the probability that my xv minus yv being positive or negative. Let's ignore the tie case. Yeah, let's just cheat a little bit more. So according to the sign of xv minus yv, I'm gonna color my vertex v by blue or red. Yeah, so this is the toy model. And what do we do? Well, we have a bunch of independent random variables, so we can do some normal approximations. So the expectation of my xv minus yv is basically b minus r times p. Okay, so basically this is the discrepancy in the previous step. And hence I can write this as, so if I write MIPT for the normalized discrepancy, so I just divide this number by n. Yes, then it's basically n times MIPT times p. And what's the variance? So the variance would be roughly NP. Yeah, I mean NP1 minus P and some constant factors, but let's say P is literal of 1. So let's say this is basically NP. Okay, then what happens in the normal approximation formula is if the xv minus yv being positive, say, is the probability that a standard normal variable is greater than minus np mu t divided by square root of np. Yeah, and that's roughly half plus square root of np times mu t. And that's what we exactly expect. So we expect that this would become mu t plus 1, which is the t plus 1 step normalized bias. So if we repeat this process, then what will happen is the number of blues will increase as we proceed, like this. Yeah, and hence we have, as long as we have NP tends to infinity, the bias would converge to its maximum possible value, which is n. And that's how they expect it to happen. Yeah, and our lemma just states that this heuristic is true for day 2. If we are on the range. So let me just ignore the constants to speed up my writing. Yeah, so this is our key lemma. So, I mean, there's a similar kind of estimate happened also in this paper by Fontolakis, Kang, and McKay. Yeah, but we managed to prove this heuristic for a sparser range of P. So what do we expect? So initially, we'll have the discrepancy of roughly square root of n because of the standard deviation coming from the random ±1 assignment. And then if we multiply square root of np, then we'll get n times square root of p. And then if I multiply this again, then we'll get this number, n to the 3/2 times p. So what we expect for the day 2 bias is exactly this number, n to the 3/2 times p. Okay, how much time do I have? Probably...
You have 3 minutes plus 5 minutes for questions, so
okay.
You can decide how to use that.
Yeah. So let me just explain a little bit about our proof step strategy. So our strategy resembles these sharper models suggested by Tran and Vu. So our strategy is to consider the parallel universe, which sounds like sci-fi, but yeah, so nothing really special. So here, our R naught is the ±1 assignment as equal as possible. So you can just fix such a ±1 assignment, or you could do it randomly. So these are all equivalent. So we just assign ±1s as equal as possible. And we sample GNP, and suppose we play these majority dynamics with these R naught instead of S naught. Okay, and then we'll get R1, R2, and so on. And then what I want to do is to, after R naught, what I want to do is turn square root of n -1s to +1s. Yes, so firstly, we put these ±1s as equal as possible. And I'm going to choose the random, I'm going to choose -1s randomly, right? The subset of -1s randomly to turn those vertices from -1 to +1. And this new assignment, S naught tilde say, this is to resemble, this is to mimic the behavior of the original problem, S naught, S1, S2. Because here we have this square root of n discrepancy to start with. Yeah, so, and what the way we do, the way we analyze this is to keep track on the effect of these swing vertices. So like swing voters, swing vertices we call. Yeah. So we prove that by the effect of these swing vertices, Yeah, this lemma is true. Okay, let me just give you a very rough sketch for that. I should probably skip this tedious second moment estimate, but let me just, yeah. So this is a key definition. So I'm going to say that my vertex V is almost positive if in this setting, in this parallel universe, the sum of R1s in the neighbor is almost positive. So is that it can be minus, it could be minus, but not too much. So these are the candidate vertices that really receive the effects of the swing vertices. Yeah, and the key lemma, the key technical lemma of ours states that there are many almost positive vertices. So how many? This many. Yeah, so there are slightly more than half vertices that are almost positive. And this number here, p times n to the 3/2, exactly corresponds to the number here. Yeah, so we engineer those numbers in such a way that they match. Yeah. Yeah, and then what happens for these almost positive vertices? Well, they can have some special type of red neighbors, which have the special property as follows. So in the neighbor of those red neighbors, so it's basically the second neighbors, it could be the case that it has the same number of red neighbors and blue neighbors. And we also analyze the probability that there's a swing neighbor in this vertex. So this swing neighbor is enough to change the color of this red vertex here to blue. If we chase the effect of the swing neighbor, then it would turn blue. And because these special vertices will turn blue, and there will be, we prove that there are at least p times n to the 3. So what was the definition of almost positiveness? Yeah, p to the 3/2. Sorry, I'm confusing myself with numbers. Yeah, so p to this, yeah, so the number of these special red vertices is at least some constant times p to the 3/2 times n. These almost positive vertices will turn blue on the second day, no matter what the color was on the first day. Yeah. So I'm seeing, okay. Yeah. Yeah, so this is the strategy. And let me just wrap up quickly with open problems. Yeah, so the conjecture of these 5 people remains open. So it remains open. And there's a conjecture by Tran and Vu saying that we can put the discrepancy of ±1 as small as possible. And then the GN half will converge to unanimity with probability larger than a half. Yeah, and this was recently proved by Ashwin and MIPT. Yeah, so this is settled. But this conjecture remains open, so it would be interesting to explore if these new ideas can bring something for this conjecture by 5 people too. Right? Yeah, thanks. I'll stop here.
Thank you, Joonkyung. Let's thank Joonkyung. Okay, we have time for maybe 1 or 2 quick questions. Okay, I see no question.
Yeah.
you have further comments, go ahead.
Yeah, maybe you might be curious about the number n to the 3/5. Why this number happens?
Yeah.
Yeah. So it just comes out of the second moment method to prove this part here. Yeah. So maybe the real problem happens if p is smaller than n to the minus 2/3. So this may be like much harder. And we kind of think that it might be a bit easier to, so this look quite, let's say, like this more or less look like a technical barrier. So if we could refine the second moment method or the way we apply the second moment plus Berriesen in this proof of ours, then we might be able to go beyond this. I don't know. But this seems a much tougher barrier for the next next step. So yeah, but the conjecture itself is for to recall p being asymptotically larger than 1/n. So yeah, I think there are lots of work remaining. So
Okay, thank you.
Actually, I have a very quick two very quick questions. So what if you add a bit more randomness in this thing? Like, for example, well, one thing I guess that wouldn't influence anything is allowing, in case of equality, to resample the vertex. And one maybe to introduce some noise in this whole thing, like allowing a very small proportion of things to be resampled.
Yeah, that's
vertices or edges, I don't know.
Yeah, that's an interesting question too. I've never thought about that. Yeah, but what I expect is unless you perturb your setting in such a way that it kind of changes the numbers, the discrepancy itself, then what I expect is that it should behave like essentially the same. Yeah, but it's an interesting question. Yeah.
So maybe it makes some sense to ask, like, if you in your toy model you use this edge resampling, but completely, like all the edges were resampled, right? So what if you allow to resample them, but with like much smaller probability? Where is the threshold for this argument to kind of go through?
Yeah, you can also ask for the initial bias to force the unanimity as small as possible. Yeah, so that's another thing you can do. Yeah.
Thanks a lot, Joonkyung. Let's thank
you.
Joonkyung.